with my previous from the paper talk that we will use now the characterization data from the workflows and we apply it in our simulator. So I will show you how can we use the data, and then we can simulate. Let's say we measure some execution from one region, and then we estimate the execution in another region, including data awareness, as I mentioned earlier. So just to show you, this is, let's say, one workflow. Important is that each function has some instances, some 30, some 141, and then we need to measure how many files each function downloads and how many files each function uploads. And then using our mathematical model, we can estimate the data transfer between regions, between different regions of function and the storage. And this is our setup that we prepared for this demo. So if we use Innsbruck, we run functions. So the red line is our execution. So we deployed montage functions in London, and those functions used data in London, and we executed and we measured only this execution. And then using this execution, we are able to estimate if we deploy the functions in Amazon Frankfurt, for example, and if those functions access to North Virginia storage. This is the so in the original version of the simulator, which we published last year, we were able to estimate if these functions in Frankfurt access data in Frankfurt. But now we extended that with our adding the networking model, we are able to estimate also this. How do we configure this? In the AFCL file, we need to first, as I mentioned earlier, we need to describe which function do we run. So EU West. So EU West is London. So we execute it in London, but we are looking our deployment, in this case twin in Frankfurt, also in Amazon provider, and with the same memory, 2 GB memory. We use this memory to reduce the instability of networking. And then we configure that we need to delete the data downloads and uploads from London to London, and to add from Frankfurt to North Virginia. So we don't need to measure it, but we need just to specify how many files does the function downloads and the total amount of time, and then the networking model uses this. With this information, we are able to, let's say, just to mention how do we measure? We executed a function that uploads and downloads files between regions, and then we measured bandwidth and latency between each region. And then we set up the simulator. These values will be the same if you would like to run it. Just the difference is the latency between, in this case, Innsbruck to London. Maybe you would need to remeasure the other data. And then the simulator would output all function for each function that is simulated. It will output the estimated round trip time. As you see, we added some deviance, slight deviance, and also it will show the total the total workflow execution time. In this case, I simulated London, 47 seconds, but the where is the slides? Just to this one. So the results, learning from London. So from 47 seconds, as I showed, we estimated, so this is the simulated with the dashed line, we estimated that 220 seconds will be execution from Frankfurt to North Virginia, and the solid line was real execution. So you see that it's enough just to run only this, and then we estimate how closely we are at around 97%. So this demo is online available, GitHub www.xafcl. You can download and test. Okay.
Any questions?
Thank you.
No questions? Then we can go to the next presenter, which will be remote. Tomasz, can you hear us?
Yes, I can hear you. I'm trying to share.
We can see and hear you.
Okay, I'm sharing screen. Is it okay? I will try to do it in 5 minutes. It's difficult. 5 minutes. So my talk is more or less a short talk than the demo, but it's some sort of proof of concept in the middle. So in this talk, we'll talk about the challenges and opportunities stemming from heterogeneous computing nodes in the resource-constrained edge computing clusters. My name is Tomasz Szydlo, and I'm working as associate professor at AGA-GOST in Kraków, Poland, and also as a senior lecturer in the School of Computing, Newcastle, UK. So in the talk, we are focusing on the edge clusters composed of resource-constrained devices as presented in the figure in a red box. Such an edge clusters might be composed of devices as Raspberry Pis, NVIDIA Jetson Nanos, and the other single-board microcomputers. Most of them are based on the ARM processors and might contain various neural network processors to speed up the inference process on the devices. However, these embedded devices might compose edge computing clusters. There are several lightweight Kubernetes distributions that might be used in this case. They have limited functionalities compared to the classic full-fledged one and are optimized in terms of resource consumption. However, we think that schedulers in the Kubernetes clusters should be aware of physical aspects of the device and the environment in which they are working. As an example, information about the electric power quality, vibration of the cooling fans, dust level, and the other parameters should be taken into account during work scheduling, especially in the edge use cases where we are deploying these devices in the hard-to-reach places. At the same time, the lightweight edge clusters should be optimized to be power efficient. Therefore, additional level of power control of the nodes should be useful. So the extended control of the hardware and the awareness of the physical context in which these edge clusters are working opens a plethora of new use cases and edge clusters. There are open research questions driving the future research, which are the questions related to how to manage, prevent compute speed degradation due to the CPU thermal throttling. This is the aspect commonly omitted in the research papers, because when one of the nodes is overheating, the processor just degrades its processing frequency and reduces the processing capacity. Then the question is, which mini Kubernetes distribution would be the most suitable for hardware-aware extensions? And how to incorporate predictive maintenance techniques into Kubernetes scheduling, informing the owners that something is going wrong with the edge clusters. The other research area worth to explore from our perspective is what is the benefit of scaling below zero. It's the term that we can discuss on with Alec from IBM, of course. The idea is that disabling the computing nodes might be of some interest in terms of processing power. So it would limit the power consumption because the rule of the thumb is that the power consumption of the node in the idle is more or less 50% of the power consumption at full processing power. Of course, the drawback of controlling on-off power is that booting the node might significantly affect the processing time and cold start of the services. Of course, in this case, we need efficient load prediction algorithms to make decision when we should power the nodes and at what time. Of course, heterogeneous computing modules enable also scenarios where pods could be located on the nodes depending on its processing speed. So having various capabilities of the nodes, we can reschedule the processing to these nodes. And another opportunity comes from the fact that the machine learning models deployed on these modules might be optimized and adjusted to the node's capabilities and invoked depending on the status of the node, status of its power and the load and availability of these nodes. However, if you would like to control the power of the nodes and get the information about the external context where these edge clusters operate, we need some extra dedicated infrastructure for processing this data. As an example, what we can find on the market nowadays is a Turing P board that contains network switch, power management of the boards, several I/O ports, and 4 slots for computing modules like Raspberry Pi compute modules or NVIDIA Jetson Nano nodes that we can put on this motherboard. What is interesting, this Turing board is equipped with a microcontroller inside that runs hardened Linux and provides command line interface through which we can control the power of the nodes. There is also option to control this motherboard remotely by connecting to the controller through the network using SSH. And of course, one of the interesting opportunity would be to control the nodes by modifying their processing frequency and the clock of these modules, just to control the power consumption and the processing throughput. What we did till now, we're working on in-lab prototype of edge cluster equipped with various environmental hardware sensors. So in this case, power measurement was performed by the Texas Instrument ENA 219 sensor, and the data were processed by the external Raspberry Pi Pico board. In the figure that we have on the slides, we can see the starting process of the edge cluster. After powering it on, the components on the main board are activated. This is the networking switch, cooling fans. Then in 2-second interval, computing modules are activated, what we can see on the slides. This is to prevent power peaks during system startup. The similar approach is taken during the system shutdown, what we can see on the right side of the chart. In the current prototype, data from the power measurement sensor and the vibration sensor is processed by the external Raspberry Pi Pico board, but in the future it can be processed by microcontrolled deployed on the motherboard. Of course, there is possibility to utilize a TinyML anomaly detection algorithm for detecting anomalies in the power profile of the cooling fan. To sum up, edge computing and the edge AI and TinyML are gaining momentum. So we can observe even during the slides that we had during this workshop. We think that low power edge clusters should be composed from heterogeneous processing modules. It will enable several possibilities such as fine-grained workload management, power control, and improved redundancy. Of course, taking into account the high demand and flexibility of the cluster management provided by the Kubernetes, the future research should focus on holistic scheduling of the cluster, using also the information of the hardware state and possible failures and anomalies detected in the system. So thank you. It was the last slide. I hope that I managed to fill within 5 minutes. So I'm open for the questions.
Thank you, Tomasz. Any questions from the audience? You can always ask questions in Discord or later on contact Tomasz. I think the next one is Josef. Are you ready to show your talk? Yes, Tomasz, make sure you stop sharing. Right?
Yes, I have stopped it, so it should work for Josef.
So thanks. Hello, everybody. Sorry, I cannot be there in presence in Bologna since I had teaching until 5 today. Otherwise, I would have gone there. So my talk has around 3 times as many slides as I have minutes, so I will be dashing through them. And if you have any questions about details, you can ask me later. The topic is databaseless queries using Calcite, Apache Calcite, as a research testbed for hybrid cloud data integration. So this is the result of a secondment conducted earlier this year for 3 months at IBM Research, where the question is, how can we optimize cross-cloud workflows where a customer may have, let's say, 2 cloud deployments, some compute power in a private cloud environment, some in a public cloud environment. And we are conducting SQL queries. We are running data analysis where the result of the SQL query may be large or small. And depending on that, we have egress cost on the first cloud. So if the result of the query is very large, we may be better off transferring the data and running the query on the second cloud, as one optimization goal is to minimize data volume in order to save cost. Of course, another optimization goal is always in database technology, minimizing the make span. But here we really have both goals, and we want to look into the heuristic planning phase for creating the query plan. So we are using Calcite, which is kind of an relational database management system construction kit, in order to parse our SQL queries and understand better what relations are involved and what statistics we may expect. So I will skip most of this slide. And so we had the idea to build something as simple as SQLite, which works in memory as a simple research client on Calcite, but make it programmable so that we can bring in our own hooks. And this is the slide I already presented during WoSC9 earlier this year. And now I show what we have done since then. So we implemented a Calcite research client, not using the JDBC path as we initially thought, because that turned out to be problematic. As you can see on the right side, it does not fully work, but we went directly into the APIs provided by Calcite to create our functions, tables, views, insert data using data manipulation language commands, and then finally selecting the right metrics and producing a lot of measurement data from those queries. So here you can see a brief screenshot from the client. You can download this from Zenodo or any other website where we published it. And you can see it works just like SQLite. You don't see much of a difference. You create your tables, you insert, you select. Plus, our client supports user-defined functions. We support scalar functions that work without any external cloud service, but also scalar functions that access cloud services, function as a service, for example. We support UDAF's aggregation functions and UDTF's table creation functions that you can also combine. You see on the right side, you can make a lot of interesting experiment with SQL code, which is fully defined in code by the user-defined functions. So having that, then the question is, how can we execute our queries and estimate and potentially even optimize the network transfer size? So we are running the queries, as you can see on the left side, producing the query plan, the logical and then physical query plan, and we get some basic metrics from Calcite. Now here we come across the first issue that those metrics are completely unusable. They are based on assumptions which do not relate to the actual tables that are involved in our query. So this is poor consideration of row count and other cardinality metrics. And if we then go beyond the system boundaries, such as network traffic, egress cost, and the compute power available at our 2 different cloud providers, this is not at all handled in Calcite. So we tried to extend it. We introduced a new SQL keyword called predict. So we run predict select to find out whether or not our prediction makes sense. We first did a baseline experiment. We see that there's some basic variability of the results, even if you don't involve any changes in cloud providers or software or data relations. And with that, we have been able to test a few scenarios, such as we have a table that has a couple of input lines, and we want to see how would it perform with 500 input lines. And we see the result would be almost 700 seconds. And then we verify with the result whether or not it has that behavior, if it really contains that many input relations. In order to generate large scale tables, we also built a training set generator that produces tables with certain characteristics. Of course, that is more a side aspect. There are such generators available on the internet. We just wanted to have one which is very customizable for our needs. And with that, we have been able to generate complex scenarios. You see a couple of tables here that are generated and that also ship with example queries that can make use of the synthetically generated data in order to find out whether or not the prediction is helpful. And the final outcome of the project was that if we have a lot of training data with fine-grained bin sizes, then we get very high, very good accuracy rates. We can really predict what will be the egress traffic from a certain cloud database service. It depends a bit on the service implementation. You can see on the right side that, for example, MySQL has typically smaller IP packets or content compared to PostgreSQL for the same result relation. So we just need to add the scaling factor. And you can see that the overall result then led to something like 80% accuracy for the execution time and 85%, the blue line, for the data size. Now, that concluded the secondment. The next steps would be then optimizing, understanding the characteristics of the cloud providers. That is not quite part of the work. So we focused on building a framework based on Calcite that enables such research to be done, and we got the first numbers. So based on that, we can now activate the placement of computation. Maybe we have a Kubeflow workflow where we can shift queries around. So this would be the next step. So thank you very much for listening. I have been brief on purpose, I hope, and feel free to ask any details that you may want to know about the work.
Thank you, Josef. Any questions from the audience? Yes.
Thank you for the talk. What happens if you cannot fit the entire data set in a single function?
The function is invoked row-wise. So in the standard scalar UDF model in Calcite, the function instance is per row of the table. So the only risk would be you have a very wide row. And then, of course, you cannot invoke the function. Yeah? So if the function takes a maximum payload of 1 megabyte, as some of the FaaS providers do, then if your row is, let's say, one row, one column, so one data entry is too large, it's larger than that, then you cannot call the function, obviously. And it will return a null value.
Thank you.
Any other questions? If not, you have the last.
Okay, this talk will be about a slightly different topic that we started this year to research again in federated clouds, but now with backend as a services. So engineering serverless workflows with interoperable BaaS services. So serverless is function as a service plus BaaS as a backend as a service. So functions may, as we saw earlier in one previous talk, functions may call external services. They can access to storage or call text to speech or some text to translate and so on. Different cloud providers offer the same service. So speech to text, for example, Amazon offers transcribe while Google offers speech to text. But what is the problem? Some features are supported by both providers, for example, audio encoding, but then only Amazon users can use SRT subtitles, or only Google users can use spoken emojis. So different features for the same service. So if we would like to code both, if we use, let's say, some driver approach like Apache libcloud, for example, then if we switch from one to another provider, we will lose subtitles SRT, but we can have spoken emoji. what we would like is to have both options from both providers and some easy development. So we would like to have, let's say, if also depending on the input data, if the input data is on Amazon, but we want to have some feature from Google, then we would like to create only one object and then specify my input data is here. And I would like this format to be used over my data. Or if we have two features that are different, that are supported by different providers, we would like to have, I want to add SRT subtitle true and profanity filter true. The first one is supported only by Amazon, the second one only by Google. But as a developer, I don't want to take care with who supports what. I want to code only these two lines of code. And for more advanced users, for example, Amazon is more accurate than Google or vice versa. I would like maybe to specify, I want to use Amazon service for this. So I would like to specify maybe provider directly for my goal. And therefore, we would like to create some serverless intent. We call this some code name, where we would like to create an intent, what we want to do, not where or who to do that, which provider or which service. So we would like to have all three as a union of features, not as an intersection between the providers. And for these purposes, we have developed already one very big library core in Java, which supports 4 different services, and those are these 4. So speech to text, text to speech, translate, and OCR. So we offer a single interface to the developers. Also, we have in Python and in Go. And also using this core library, we developed 2 workflows, PDF to speech and speech translate. A workflow that converts multiple pages of a PDF into speech, and even it translates from English to German, for example, or speech to speech translate from English into German. Why we did this composition? Because there is no single service from Amazon or Google or any other provider that converts, let's say, that translates audio into audio. So using our AFCL, we can convert this, and of course using this library. Okay, I'm done. Yes. I tried to be on time. Yeah.
Thank you. Any questions to present? Okay, thank you. Nathanael, we have you next. Can you hear us?
Yes. So.
Okay, very good. I will play a quack sound, you know, when you close to 1 minute, because I think people are getting really tired right now. So keep that in mind, you know, and go ahead.
Okay, I hope you can hear me. Perfect.
Yes, we can see your slides and we can hear you very well. Thank you.
Okay, perfect. Thank you. Okay, hello, my name is Nathanael Nussbaumer, and today I want to talk about generating synthetic Ansible programs with probabilistic methods. Before we get into the topic, I want to quickly thank the CloudStars program and IBM Research for the secondment opportunity that made this whole project possible. So let's get right into it. Why do we even want to generate Ansible programs synthetically, and why are we talking about this in this context? Well, Ansible is quite often used for cloud orchestration and for managing infrastructures. As such a viable tool in this area, we really want to improve the developer experience around it. When we talk about improving developer experience these days, we quite often talk about large language models. That is because LLMs like GitHub Copilot or Amazon Code Whisperer have shown great success in helping developers write code faster. But these LLMs have one big drawback, and that is that they need a lot of data. That is not such a big deal for popular languages like Python or JavaScript, where there are a lot of open source projects readily available for training. However, in Ansible, we don't have this luxury. So we need to find another way to get more data. And for this project, we try to generate it synthetically. So let's quickly look into how an Ansible script looks like. And you see on the left side of the screen, it's basically just a YAML file, and we call it as programs playbooks. Each playbook has one or multiple tasks, and each task runs one Ansible module. And each module has multiple parameters. The parameters are actually the focus point of this talk, because for us, it's a bit out of scope to generate the whole Ansible program. Also, it's quite hard to validate if the program is correct, not only synthetically, but really, really correct. And so we want to focus on generating good values for these parameters. Also, one thing to note, we have, for some modules that are more popular, like YAM, for example, we have a lot of data, but for others, we don't have that much data. And the idea is to transfer the data or the knowledge we have about the more popular modules to the less popular modules. To show you our approach, let's talk about the project goals first. So as I told you, we want to generate meaningful synthetic values for Ansible parameters that can be used in templates. We want to build an end-to-end pipeline for synthetic value generation, where we can even generate values for modules and parameters we've never seen before. And of course, we want to evaluate and compare our results, and we want to especially focus on the evaluation of different models and model combinations. So now let's go through a quick example to better showcase our approach. Let's look at the module MySQLDB. In this module, we have a parameter called logImport, and we have the information that it's an integer from the documentation. So this tells us that for the logImport, we have the valid set of integers as allowed input. Let's look at another example from the BigIP monitor HTTP module. Here we have an almost similar named parameter named port. And this time the documentation tells us that it's a string. Unfortunately, this tells us absolutely nothing about what is supposed to go there. And also, if we think back about the logImport, when we're thinking about ports, we don't really want every possible integer as an allowed value, but more like all possible integers between 1 and 65,000, which is the valid range of ports. To get there, we will use the documentation, the description of the parameters and the modules, and we will use it in a way where we feed it into a topic clustering algorithms, or more, we have multiple different topic clustering algorithms we're trying. And from there, we get a distribution of how likely each of these parameters is to belong to one topic. For example, we see here, both of these parameters are very likely to be in the third topic. Now just focus on the logImport for simplicity. We want to get this information into a probabilistic model, where we then can sample a new value that may have been seen for logImport before or may have not. For example, here we sample from MySQL user, which is a different module than MySQLDB, value also called logImport, but with the value 5432, which would be an allowed port, and is also by coincidence the BOSCA default port. All right, how far have we progressed with that? Well, we've finished building the end-to-end pipeline, and we've integrated multiple clustering algorithms. We also developed our own modification of LDA that we use for topic modeling, and we've also created multiple probabilistic models for sampling. However, we are not quite done yet, unfortunately. We are still not finished with evaluating the different combinations of models and clustering algorithms. And as you can imagine, some of these need quite some time in processing, and with all these combinations, we're not quite done yet with them. And we are still waiting for the full evaluation of the results, but I hope that we can provide them to you soon, and then we can publish our full results. And in the meantime, thank you for your attention, and I'm happy for any questions.
Thank you. Any questions? If not, we will go to the next speaker, which I think is Antonio. Can you hear us?
Yes, can you hear me? Can you see me?
Yeah, I can hear you and I can see you. Can you start screen sharing?
Yes. Can you see the screen?
Yep. Looks
Okay.
good. 5 minutes.
Great. So, hello everyone. I'm Antonio Martinez Ibarra. I work at the University of Murcia as a researcher. I have recently started my PhD in computer sciences, and I'm going to briefly describe what I do, which essentially consists of applying machine and deep learning into these lines of work. The first line of work that I'm going to talk about is marine sciences. We are working on a national project for the protection of marine ecosystems, and in that regard, we are focusing on the application of AI for the understanding of a regional lagoon called Mar Menor. More in detail, I am working on predicted time series of a water level, as you can see here, nutrient flow, and the relationship with the quality of water in the lagoon. We are using LSTMs and also tried other deep learning mechanisms to predict those variables in different time horizons. The next line is smart agriculture, and it is related to a collaboration with an enterprise. On the one hand, I have used images from Sentinel-2 to apply to a set of parsers the optical trapezoid model, or OPTRAM, a mathematical model to estimate the humidity of a crop, taking advantage of remote sensing. And on the other hand, and also with Sentinel-2 images, I have been working on developing a machine learning model to estimate the normalized difference vegetation index, or NDVI, taking only RGB images. The NDVI is an index that is usually considered as a precise indicator of crop health. And the idea behind this work is that most higher resolution satellites can only take RGB images. So with that, the same amount of information would be available than if we had multispectral cameras. And lastly, in the agriculture area, I have been working on applying the segment anything model from Meta to automatically detect insects in images. And here you can see detection in an stage scenario and then in the real case. The following line is related to energy efficiency, and here we dealt with time series for demand flexibility in buildings, in particular this one. We had a large amount of data, consumption, temperature, HVAC parameters, and meteorological data. We did an exhaustive study of deep learning algorithms utilizing multi-layer perceptron networks, LSTMs, GRUs, etc., and made models for 1 and 2 hours time horizons to predict energy consumption and also room temperature. And the process dataset has been published as a data descriptor in Nature's Scientific Data, and the whole process about demand flexibility is under review for patenting. The last area I would like to mention is dimensionality reduction applied to multivariate time series. That is done using an algorithm called multivits. We dealt with several open multivariate datasets and applied that method to reduce them and compare the accuracy that we can achieve versus the raw datasets in a time series classification problem. The results are promising since the algorithm is able to reduce the time it takes to process the dataset while maintaining or even improving accuracy. And the paper derived from that research has been published recently. And finally, I'm going to point out what is going to be done as future work. Following Aurora Gonzalez's work on IBM, which she presented in session 2, I'm beginning to work also with GPUs with the intention of optimizing its performance in a controlled environment for model inference on images. Being the starting point, the data collection of memory usage, inference time, etc. For future tasks, we want to use real images instead of randomly generated ones, experiment with different models for image processing, explore GPU's behavior with concurrency, and define an optimization model and a method to validate its decision process. Here are some references. And if anyone has any doubts, you can ask now or contact me by email at the address. And that would be it. Thank you for your time.
Thank you, Antonio. I think we have to move on.
Okay.
So
No problem.
please, if you have any questions, ask them in Discord to Antonio. Pablo, can you present your talk?
Yeah. Let me share the screen.
Thank you.
Can
We
you hear me?
hear you very well.
Yeah.
I can see your screen now. No,
No.
it looks like Antonio's screen. Antonio, can you stop sharing? Good.
Okay.
Okay, now I think it's your talk. Go ahead.
Okay, so hello everyone. This is Pablo Fernández. I'm a PhD student and a researcher in computer science at the University of Murcia. And I'm giving this presentation to briefly introduce my main research line. Basically, I'm dedicated to federated learning applied to intrusion detection in several sectors and environments. That is generally what my thesis is about. So first, I'm gonna talk about some basic research on FL that I've been doing, and next, I will discuss and present some of the research articles that I'm working on or that I have already published regarding federated learning-based intrusion detection applied to different environments, and also some future work points that I'm planning to address soon. So starting here, you have a figure that we prepared for our first article about this, in which we compare and outline the main aspects of federated training with respect to centralized and distributed approaches. In a nutshell, what we get is a fully decentralized training scheme where the privacy of the data is preserved, since it never leaves the device, where the computation needed for model training is distributed across the devices, where we potentially have access to larger amounts of data, and finally, that could enable the deployment of final detection models closer to the user, reducing the detection time. Along with the pros, we also outlined the challenges and directions of federated learning applied to intrusion detection to the Internet of Things sector, which is the one that we consider for this study. For example, the fact that although data never leaves the device, and man in the middle could still infer some information from the models being exchanged, and some other problems related to bottlenecks or communication requirements and so on. Then, apart from discussing the pros and cons, we also compared in this study the training accuracy throughout rounds of training based on a multi-class probabilistic classification model using different aggregation algorithms and different data distribution from the DonIoT dataset that provides training samples from both betting traffic and traffic from different types of common attacks in IoT networks. Then in our second article, we tried to address the challenge of information leakage from model updates that I've commented previously by using differential privacy and noise adding mechanisms to basically make it harder to infer any information from them. And we propose a workflow integrating this and also tested and compared in terms of accuracy different noise adding mechanisms and measured the impact on accuracy using different privacy levels. Here you can see the accuracy throughout rounds for every mechanism and for the aggregation algorithms that we consider. Next, we apply federated learning also to the financial sector to detect fraudulent transactions in the context of the CyberSec for Europe research project. We performed the evaluation using a multi-layer perceptron for classification with federated learning training over a synthetic fraudulent transaction dataset. And we propose an architecture integrating this with MISP, a cyber threat intelligence platform for using threat information coming from outside for training, and a blockchain to preserve critical information for later auditing purposes. Basically, We measure once again the impact on accuracy that would have using the fraudulent transactions training samples, but suppressing digits from the transactions, origin and destination accounts, assuming that we would receive this information and the information this way from MISP. And lastly, our most recent work, in which we proposed the automatic and real-time deployment, configuration, and management of FL entities for intrusion detection in beyond 5G networks based on policies. That is what we call policy-based orchestration. We propose both proactive and reactive workflows for orchestrating intrusion detection based on federated learning, and also crafted a policy for deploying and configuring the FL entities that you can see here in this slide, in which we can specify lots of information for configuring both the FL agents and the FL aggregators needed. Then lastly, as future work, we are planning to generate our own dataset from the UMU 5G testbed, considering not only user, but also control plane attacks, and use it for the model training. Also to explore the applications in the intelligent transportation systems environment, the evaluation of what we have just described, the dynamic orchestration and detection, and integrating it with the monitoring and mitigation agents to come up with a closed loop for automatic and real-time intrusion detection. And lastly, keep researching about new topics such as decentralized FL and how to optimize our current implementations, for instance, regarding the models and data processing techniques used. Here you can see the references that I've used during the presentation. And this is the end. In case you have any questions, don't hesitate to ask them. Thank you for listening.
Thank you, Pablo. Okay, and our last remote speaker, Carlos, can you hear us? Carlos?
Yes, sorry, I was trying to share my screen.
Can you start screen sharing?
Yeah, I'm on my way.
So as a reminder, all talks, slides, I think are available from our website. And I think also some number of talks, we have the video recordings, like longer version of talks. So please check those out. Go ahead, Carlos.
Yeah, hi, thank you, Alec. So as some others have mentioned, the work that we're presenting today was performed as part of a secondment at IBM Research. So thank you very much to everyone who made that possible. And today's talk is titled Serverless Confidential Containers, Challenges and Opportunities. And it takes a slightly different approach to the other serverless presentations, very interesting presentations that we've seen today, which is that interfunction isolation. This is one of the big topics that has driven serverless research, as in what kind of isolation mechanism we use for serverless functions is fine, but not enough. In a modern multi-cloud or multi-tenant cloud environment where the same Knative runtime may execute different services for different functions, isolating different functions as different pods or default pods using Knative may not be enough. So whenever a user, as a reminder, we've talked a lot about Knative, so I'm skipping a bit the Knative introduction. But whenever Knative wants to spawn a new service pod, it will do so collocated in the same Kubernetes node, and the Knative controller and the Knative service will be isolated using regular pod namespace isolation. We claim that, or our observation is that we also need, not only we need isolation between different Knative services, we also need isolation from the host environment. This is all the Knative control plane management processes. We need so to preserve three key aspects. One being data confidentiality, i.e. preventing that other processes see what data is being processed inside the Knative service. Code confidentiality, maybe with some machine learning models, they have IP present in the code, maybe the model weights, and we don't want the Knative runtime to be able to leak those weights. And even more essentially, execution integrity. We want to have some cryptographical guarantee or some assurance that Knative is executing the serverless function that we want and not another one. And we're being built for what we've actually been using. To do so, to guarantee data confidentiality, code confidentiality, and execution integrity, we use confidential computing. Confidential computing allows the creation of hardware-protected areas in the main processor that we call enclaves, where the data being code executing therein are protected from any other higher privileged software running on the same physical node. So in this work, or the proof of concept that we generated during the secondment was a port of the Knative serverless runtime running on top of confidential containers, an isolation mechanism that allows the creation of container-looking virtual machines with runtime memory encryption. So I will now dive a bit in more detail of the architecture that we've built to understand what are the security mechanisms that we provide. In essence, when using Knative by default, Kubelet through containerd and the runc shim will execute different pods using regular namespace isolation. In contrast, when using our prototype, we're using a special shim v2 interface that talks with the local hypervisor and executes different Knative services inside different CVMs, which stand for confidential VMs. These are virtual machines whose memory pages are always encrypted whilst on DRAM and are only decrypted when entering the CPU chip. We also use an external third-party node to provide keys and attestation mechanisms. In order to evaluate the feasibility of a proof of concept, we want to know, by using these enhanced security mechanisms, what's the impact that this has on cold starts, warm starts, and instantiation throughput. We compare with baseline runc that isolates Knative services using containers, but we also compare against Kata containers, which uses virtual machines without runtime memory encryption to isolate different pods. We want to know, just as a proof of concept, where do we stand? And the truth is that by running Knative services with confidential containers instead of regular Kata containers, we bump cold starts from 7.5 seconds to 17.5 seconds. This is because starting the pod is 4 times slower, pulling the images is 2 to 3 times slower, and there are no warm starts. We will only talk about points 1 and 2 today. Starting the VM is 3 times slower due to the enhanced runtime memory encryption that the hypervisor, in this case QEMU, needs to perform. In addition, we found a bug in the virtual firmware driver initialization that was introducing an additional 3 to 4 extra seconds. Pulling images is twice as slower because if we want to maintain the confidentiality and integrity of the image that's being used inside the confidential virtual machine, we need to pull the details of the image inside the guest. These image details, this image pulling then is serialized for each different image that runs in the same pod. This could be avoided, and we plan on fixing it in future iterations. Additionally, the images that we are using are encrypted whilst at rest in the container registry. So we also need to decrypt them, which introduces an additional overhead. Lastly, and to wrap up, the impact of using these confidential images inside runtime memory encrypted protected VMs also introduces a high overhead in function concurrency, where starting 16 concurrent functions takes more than 3 minutes. This is because the local registry is throttling a request when each pod tries to pull an image inside the guest. In summary, using confidential containers for serverless runtime, serverless functions introduces a lot of overheads, but still some of them have easy to fix solutions, which we plan on doing so in future work. Thank you for your attention.
Thank you, Carlos. I think we are really getting to the end. There is one more talk that somebody could not come, so I will just leave you with a really short advertisement for the talk, which is to show you a few seconds of it. The full talk is recorded and available online. So challenges, opportunities, and then if you want to find out what they are, challenges and opportunities, I'm afraid you will have to go online and check it out. Thank you, everybody who came to our workshop. I think we are tired, so I think we should be closing, right, Pedro? One about future, we will be sending results of those best papers. Okay, so we know kind of already who will be the winner, okay? And about a week from now, I will also send a link to a recording YouTube, and hopefully we see you in the future.